All right, we've taken a look at equations and properties of equality, so now we need to take a look at inequalities and how to solve some basic inequalities. So in this section, we're just going to focus on those properties and then some basic inequalities. Um, so again, like I just said, in the first chapter, we took a look at quite a few of the properties of the real numbers and then some properties that involve two expressions being equal to one another. So now we're going to review properties where two expressions are not necessarily equal. So maybe greater than each other, less than, greater than or equal to, or less than or equal to. So that's what we're going to take a look at in this section. So we'll just review the four types of inequality. So let's have x be a variable. It'll be a real number, but it'll be variable, so it could change. And we'll have c be a constant, and that constant will be a real number. So the variable x could be greater than c, so that would represent all real numbers that are bigger than this number, c. So x is greater than c. So on a number line, wherever c is on the number line, the way we would represent that visually is we would put an open dot on c to let the reader know that c is not included, and then we would shade all the numbers that are actually bigger than c. So when you look at this number line, basically all of the values right here on the number line, so right here on the number line, all of those numbers would solve this inequality. If you plugged any one of these numbers, where I just highlighted it yellow, into this inequality, it would solve it, because you'd be plugging in a number that's bigger than c. Well, maybe the variable x is less than c. So the variable x is less than some number c. So wherever c is on the number line, we want to be less than that. So we put an open circle to let the reader know that c doesn't count, because c itself is not less than c. c is equal to c. So we want numbers smaller than c. So we put an open circle and then we shade to the left. So again, on the number line, that would be represented by any number right here on the number line. So if you pick any number right there on the number line to the left of c and plugged it in for x, you'd have a true statement that that number really is less than c. Well, we also have our good friend greater than or equal and less than or equal. So maybe it turns out that the number that's going to get plugged in for x, so remember x is variable, can be any real number, but we want x to be greater than or equal to c. So it's very similar to greater than, except for the option of being equal to c is there. So on the number line, it would look the same, except for we would put a closed dot on c, because now c would actually solve this inequality. Because if I plug c in, it is true that c is greater than or equal to itself, c. That is a true statement, because it would be equal to. But you could also have less than or equal to. So you would just, again, visually, it would just be c or any number to the left of c. Again, c would actually solve this inequality, because if you plugged it in, it is true that the number c is less than or equal to c, and the equal to would be the one that makes it correct. So we have greater than, less than, greater than or equal to, or less than or equal to. Well, let's go ahead and actually work with some specific ones. So our directions are to graph the following on a number line. So we have x is greater than -3. Okay, so this basically represents, so this represents all real numbers greater than 3, -3. So visually on a number line, what that would look like is, if this is our number line, so this is every single x value, let's say that's 0, -1, -2, -3, -4. We want all the numbers greater than or to the right of -3. So what we do is we go find -3, we put an open circle, and then we shade to the right, because we want greater than, that would be to the right. So basically, any number right here along the number line would solve that inequality. For example, if you pick 0, 0 is greater than -3, that's true. If you pick 1/2, 1/2 is greater than -3, that's true. But if you come over here and pick something that's not shaded, like -4, -4 greater than -3, that's false. It's a false statement. It's not true at all. Well, x is less than or equal to 14. So this statement represents all real numbers less than or equal to positive 14. So on a number line, see what that would look like. So if this is every single x value, we need 14. So let's say that's 0, and let's have this be, let's see, 5, 10, 15, 20. And we want less than or equal to 14. So 14, let's see, 14 would be just one less than 15, so this would be 10, 12 and a half, so 14 would be in here somewhere. And we want less than or equal to. So we would just mark it and go less than. So we put a closed dot because positive 14 does actually solve this inequality. If I plug in positive 14, it is true that 14 is less than or equal to 14. That is definitely a true statement. If you want to be more precise on your number line, you can. You'll just have to remember that you just have to scale it a little differently. So if you're working with large or really small numbers, just scale it. So if this is 0, you could do 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. And then less than or equal to 14 would be 14 and less than. So that's just if you want to be more precise with your number line. It's up to you. All right. So what kind of things hold true for inequalities? Well, let's find out. So we'll call these the properties of order, because inequalities is basically what lets us put the real numbers in order. So this number is less than this number or bigger than this number. So let's have A, B, and C represent any real number. So we need 3 different numbers, so we'll use A, B, and C, but they could be any real number. So in the real number system, when you have 2 real numbers, exactly one of the following could be true. If you have 2 real numbers, either one of those is less than the other one, equal to the other one, or bigger than the other one. So if you grab any 2 real numbers, then one's either smaller than the other one, equal to the other one, or bigger. Only one of those could be true. The next property is the transitive property, very similar to the one we've already studied with equality. Basically, if you have 2 real numbers, A and B, if A is bigger than B, and it turns out that B is also bigger than some other number C, so A is greater than B, B itself is greater than C, well, since A was bigger than B, A must also be bigger than C. So A was bigger than B, B was bigger than C, so A must be bigger than C. And this is true for any of the inequalities. So I've got all 4 here. So if A is greater than or equal to B, and B is greater than or equal to C, then A must be greater than or equal to C. And then we have the other 2 types of inequality, less than and less than or equal to. Well, again, similar to when we did our properties of equality, we have an addition property and a multiplication property. The addition property is basically going to say that you can add the exact same value to both sides of an inequality. So if A is greater than B, you can add C to both sides, and it's still true that the side with A is bigger than the side with B. So if A was bigger than B to begin with, when you add the same value to both sides, the side with A is still bigger than the side with B. And again, this is true for all 4 types of inequality. So I've got all 4 written there for you. And then for multiplication, it gets a little trickier. So you probably remember from middle school or Algebra 1, whenever you first did inequalities. If you multiply both sides by a positive number, then nothing really special happens. So if A is bigger than B, you can multiply both sides by the same number C, and the side with A is still bigger. So AC would be bigger than BC, and that'd be true for all 4 types of inequality. But it gets a little bit more interesting when the number's negative. So when the number's negative, if you multiply both sides of an inequality by a negative number, then the inequality flips. So if A was bigger than B to begin with, then if I multiply both sides by a negative number, and then it turns out the side with A actually ends up being smaller than the side with B. So when you multiply both sides by a negative number, you end up flipping or reversing the inequality sign. And remember, multiplication and division are essentially the same thing. So this would be true for division too. If you divide both sides by a negative number, you need to reverse the inequality sign. All right. So with those, we can now actually solve some basic inequalities in one variable. So let's say you have a complicated inequality that when you look at it, and what I mean by complicated is you look at it and you don't know what the solution is just by looking at it. Well, in that case, we're just going to change it to a simpler inequality where we can easily figure out its solution set by looking at it. Now, when we do this, we want to make sure that when we transform it, each time we do something to it, the solution set never changes. So we want equivalent inequalities each time. And the way we do that is essentially the same way we do it with equations. You either simplify either side of the inequality, or you add or subtract something to both sides of the inequality, or you multiply or divide both sides of the inequality by the same number. Just remember, when you multiply or divide by a negative, you need to reverse that inequality sign. That's the thing that's easily forgotten. All right, so let's give it a try. Okay, so we have 5x plus 17 is less than 2, and you know, by looking at it, it's kind of hard to tell what values of x would make this a true statement. So what we're going to do is we'll use some of our properties. So one of our properties says that we're allowed to subtract the same number from both sides. So we'll do that, and we'll end up with 5x is less than 2 minus 17 is negative 15. And then this inequality has the same solution set as the one we began with, but it's a little simpler of an inequality. But again, you might not be able to look at it and tell the answer. So no big deal. We'll just take that one, and we will divide both sides by 5. So we'll divide both sides by positive 5. 5 divided by itself is 1, and negative 15 divided by 5 is negative 3. Well, it doesn't get any simpler than that. That right there tells you exactly which x values would solve this inequality. So the solution set would be all x such that x is any real number less than negative 3. And then they want us to graph the solution set. So if this is 0, and that's negative 1, that's negative 2, and that's negative 3, then this basically any real number that's less than negative 3 or left of negative 3 would solve this. So that would be open dot and then shade to the left. So any x value that you pull from this part of the number line, so like negative 100, negative 3.1, negative square root 11. So anything that's smaller than negative 3 would solve this inequality. So there's its solution set, and then we also have the graph of that on a number line, just to kind of visually show where all the answers are. Because it turns out there's a lot of answers. It's any number less than negative 3. That's an infinite number of answers for that. All right, on this next one, we've got 5 times the quantity 3 minus t is less than or equal to 7 minus t. So let's go ahead and isolate t, or solve for t here. So if we distribute, we have 5 times 3 minus 5 times t is less than or equal to 7 minus t. So we have 15 minus 5t is less than or equal to 7 minus t. And we need to combine like terms. So let's go ahead and add 5t to both sides. So we will just add 5t to the left side and add 5t to the right side. So we end up with 15 is less than or equal to 7 plus 4t. And then we'll subtract 7 from both sides. So we'll subtract 7 from the left side and then subtract 7 from the right side. And we get 8 is less than or equal to 4t. And then we'll divide both sides by 4. And we'll end up with 2 is less than or equal to t. So our solution set would be all t such that t is greater than or equal to 2. So the inequality, the open side, points to the larger value. So t is greater than or equal to 2. And then if we go ahead and graph that on a number line, if this is 0, this is 1, this is 2, this is 3, and so on, and that's every value of t, we want greater than or equal to 2. So it can equal to, so close dot, and then greater than would be shade to the right. So any number bigger than 2 or equal to 2, when you plug it into this inequality, we'll get a true statement. So it's an infinite number of answers. Any real number bigger than 2 or equal to 2 will solve that inequality. Let's go and take a look at one more. Let's simplify the right-hand side. So we have 2t is less than, we'll go ahead and distribute, negative 1/2 times negative 6 minus negative 1/2 times 4t. And then we have 2t is less than, negative times a negative is positive. And then we'll have plus 2t. So half of 6 is 3, negative times a negative is positive. Negative negative is plus, so we have 1/2 times 4, which is 2, and then we have our t. And then let's go ahead and subtract 2t from both sides. So subtract it from the side and subtract it from the right side. And we have 0 is less than 3. So the variables dropped out. So there are no variables left. And 0 is less than 3 is a true statement. So this right here is a true statement. And similar to when you solve an equation, a regular equation, if the variables drop out and you're left with a true statement, algebraically that's telling you that every single value of t, when you plug it in, will give you a true statement. So every single real number works in this instance. So t can be any. So since any real value of t works, we write our solution statement, our solution set, as all t such that t is an element of the real numbers. So since any real number works, when we go to graph it on a number line, since every single value of t is a solution, we just end up shading the entire number line. So if you pick any real number off the number line, plug it in for t, it'll solve that inequality. So this solution set, even though it looks fancy, this solution set right here basically is just saying all real numbers are solutions to this inequality.